Okay, so Linux security and how web browser sandboxes really work. And this I find really interesting. So this is about the Linux security APIs that have been coming in the later versions of Linux and how they are used inside of Chromium to make the sandbox of the Linux version of the Chromium browser. That means the Chromium browser, the Chrome browser, Opera browser, Brave browser, Vivaldi browser, all sorts of browsers that are based on Chromium. So probably a browser on your computer. Okay, let's get going. This is shorter, I promise.
Yeah, it's still a little new project.
Okay, I'll start slowly then. Okay, by the way, this is the dyno from Chrome. So I remember which presentation it is. Okay, so one of the things, the reason why I made this, this presentation was because I think that Linux security APIs are really interesting. And then I wanted to talk about them. But most people don't find them really interesting. So then I was like, yeah, but people think browsers are cool, so I'm going to talk about them in context of browsers. And also the fact that Sandbox sounds also very cool. And I had to pitch it to a conference, okay? They bought it. I had people came to my talk, too. Okay, so yes, this was me from before, so we'll skip it. Okay. So the Chromium family of browsers have a very specific type of process architecture, and that is very important when you're constructing the sandbox. So we're going to look at it a little bit here. So basically, the first thing that you will see if you look on your machine, there is only one browser binary. You will find oftentimes two binaries in there. One is called Sandbox. We won't look at that at all. Because it's only used in certain scenarios, and so we're going to be looking at what is used in a regular new Linux, like an Ubuntu, whatever, relatively recent. And in that case, only the actual browser binary is used. And so when you start up your browser, it will start up two other processes. And then do this with an actual exec. One, it will do a clone exec, and the other one, it will do a fork exec. The clone exec makes what I call Zygot init. And the fork exec will make the GPU process. These are started for real with like command line arguments and everything, and like for real. After that, it will only use fork and clone for making different kinds of processes. This architecture was made by Google when they took in the WebKit project from Apple, which Apple had taken from KDE, because this is the concept here. Nobody has made a really new browser since mid-90s. All browsers belong to 4 browser families. One no longer exists, or well, it exists, but it is decommissioned. It was the old Opera engine. So we are down to 3 families. We have what I would now call the Chromium family, but it includes Safari because of the WebKit heritage, and also everything back to Conqueror. And then you have the Gecko kind of family, where the Firefox, Mozilla, and now the Quantum, Firefox Quantum. And then you have Microsoft's engine, which has been IE, Edge, that family. So those are unfortunately all the families we have. But this is the Chromium architecture, which was made by Google around the WebKit project. And basically, with the architecture was built mostly as a utilitarian solution that they had when they made the Chrome browser in the beginning, is that inside of the renderer here, they had the WebKit project, which was being dumped by Apple all the time, and it was very unstable. It crashed a lot. So, and they had very little control over it. So they stuffed it in its own process, and then they made a whole system around it to be able to have to have it crash and not take down the browser. And they marketed this as a browser, a tab will crash, but not the whole browser. But it was basically it was an architecture made to deal with a problem they had in shipping a browser with WebKit inside. So a renderer here will generally be what you think of as a tab. And this part is also very interesting. The GPU process does all the composition, because here you have lots of renderers that are rendering all of your different tabs, but in the end you're going to make one window, right, with everything in. So somebody has to do the composition of all of these things that all of these different processes are making to one thing. And that's what the GPU process does, which is very interesting because this is the only one that has access to the GPU. So you have to have serialization of GL commands over to this process. It's a very interesting architecture. See, I told you it was very interesting. Okay. Anyway, so all of these things have different security aspects, and so when the good thing about this architecture is that when the architecture was made, they could also wield platform primitives to make security decisions around these, because these processes are now separate and you can treat them as separate entities with different policies. And that's what they did. And so if we're going for the thing that is least trusted, it's this thing, because JavaScript runs in there. This is actually also a little bit untrusted because GPU driver stuff. And they have also had issues with stability, right? So a Chromium-based browser will survive the GPU process crashing, which is kind of weird, but it will. What you will see is that the whole window goes black, and then you wait a couple of seconds, and it comes back. That is fancy. Okay, so anyway, so the Cygot here, I don't know, are any of you familiar with Android? Like inside, yeah? Are you familiar with the Cygot part of Android? Yeah, there's a similar architecture in Android when you're starting apps. They have this Cygot process, which forks off or clones, I don't remember in the Android case, off these things, and so they have the same thing here. So this Cygot here actually clones itself for each new renderer, and this Cygot here, which is the parent, is sort of like an init process. Waiting for all of the children. It's a very, very Linuxy architecture because this is the Linux solution. And this one is split into two because they have two parts here that have different security policies. Okay, so basically the most important thing from this slide is that everything is one binary. There's only one binary, it's just being forked and cloned. Yes? Yes. Yes, there are pipes everywhere. They have a whole IPC mechanism. And the reason for that is because they have done the sandboxing. Like, for example, there is no network access here, here, or here. This is a browser. None of this can access the network. Only this process is allowed to access the network. So all network traffic has to be piped to the relevant things. There's like a whole massive system of IPC to handle this.
Is it the same in Windows? Does it have the concept
Ish.
of cloning and forking?
No, or I don't know that much about Windows. But yes, they do split up into, on all platforms, they split up into different processes, and on all platforms, they have the IPCs. So the generic architecture is the same, but exactly how you implement the different kinds of security policies is different from platform to platform. So this is only for Linux, what I'm going to do in this presentation, but they will do these kinds of splits, but using platform primitives. Okay, yes. Okay, so we're going to start, and this is the initial sandbox. So the first sandboxing is done when you are splitting off the Cygot init process and the GPU process. Now, there are lots of things here. I went through a lot more in my original presentation. This is a little bit shorter, but basically here, when you clone. Now, okay, that's the first question actually. Does anybody know the system called clone? No. Okay, good, because it's very interesting. Okay. Clone is generally used as an implementation detail for implementing fork. How many are familiar with fork? Excellent. Okay, clone is like super fork. You can do anything you want. It has a million options that you can pass in, and actually, one of the things that you can do is with the right flags to clone, you make a thread. And the right, this is Linux, you gotta love it. So you so right flags to clone to make a thread is, among other things, share virtual address space. Isn't that cool? It's like, I'm going to make a thing, and it can share my address space. It's all right. We're friends. That's fabulous. Okay, anyway. But the cool thing about clone is you can pass lots of flags. And in this case, some of the flags that you can pass is what are called Linux namespace flags. Now, who has heard of Linux namespaces? Excellent. So if you want to create a child and you want to put this child process into a namespace, you have to use clone generally. And then you pass in which types of namespaces you want to put this process in by flags to clone. And that will do it. So in this case, the browser will clone Saigot in a user namespace, PID namespace, and a net namespace. This means that when it becomes, and this user namespace is kind of special because in newer versions of Linux, in most distributions, you can make a user namespace as an unprivileged user. So you don't have to be root. And what that means is that when the process that you have cloned into a user namespace, it will think that its user is root. It's not root. Outside, not root. Now, this is something that you have probably seen if you've used Docker containers. Docker? Yes? Yeah. Yes. Docker containers uses these APIs a lot. And actually, the container business have driven a lot of these developments of these APIs in Linux. So when you create a user namespace, inside of the namespace, the initial user is root. So now you're root. Excellent. And then you can create other things, like a PID and a net namespace, which you have to be root to do. See? So that's the trick. You start off making a user namespace. Now, a PID namespace is basically now you're saying that I can only see me. So now I'm PID1. Of course, outside of the namespace, you're not PID1 at all. You are PID something, something, something. And you are not root, you are something, something. But inside to that process, it will look like you're PID1 and your user's root. And if you make a net namespace, you have no access to network. So here, it's like snip. None of these have access to network anymore. So that's the first part. So the first snipping happens here. So now we have a process here that thinks it's root, thinks it's PID1, and has no access to network. On the other side, we're just doing a regular fork exec. So we're not doing this fancy stuff. So this one still has full access to the platform. And that's because GPU drivers are weird, and they do all sorts of weird stuff, and they need all sorts of weird things, and some of them call home. Yes. Anyway. Okay, so what we're looking for here as we're building the sandboxes, because what you realize is all of these different things get different kinds of sandbox policies, is that you have to kind of create a moment in time where you're allowed to restrict. Some things you're only allowed to restrict on a clone, like making namespaces. Well, there is something called unshare, but we're not going to get into that. Okay. Yeah, so these are the namespaces we're using. So for many new distributions, you don't need any privilege to create a user namespace. And in one, we can create a PID namespace without global privilege, because you usually need that. And then you make a PID namespace. And there you will see that you will have, and you can actually see this on your machine, but I'm not going to go into it, that there will be two different PIDs. If you look inside of the process, and it will look like a different one than outside. And then here you are isolating it from the network. And this happens to the zygotes and to the renderer, like I said before. Yeah. This is, okay, this is done in code. This is about how it's implemented in the code. It's kind of weird. Because one of the weird things about clone is if you've used fork, okay, fork is weird, but bear with me. So if you are a process and you've forked, now you have two processes who are both in exactly the same location. They are returning from fork. And the first thing you always do after a fork is to try to figure out which one you are. Okay, clone is not like that. Clone is like you pass in the function that you want. Yeah, okay, so it doesn't have this thing that it returns to the same place. It returns, yeah, it's different. So to deal with that, they kind of just wrapped it in. So they emulate a fork with a long jump, and there's like code for this that I didn't bring with. Yeah, I might have somewhere on my machine, but it's very cool. Yeah, and I said earlier that you can use clone flags to also create threads, so I'm not going to get into it. But that is one thing that's very interesting in Linux, is that threads are just a special type of task for Linux. It's like processes, threads, it's just more of the same. It's not so different. From the kernel perspective, these are tasks, and they are just have different privileges to each other. Like some people can mess in other people's memory. Yeah. So basically, they do a lot of testing to see what is allowed on this distribution, and they try to make as much as they can. Oh yeah. See, I put the code. Excellent. Okay. So they basically they make okay. So these are the flags. That's what they look like. And you just OR them together, and you pass the flags. Pass them here into this clone. I think I have it on the next slide. Okay, anyway, so you made a jump buffer over there, and you do a set jump there. Just here, inside of the function. So you have the flags and everything. Then you have to make your own stack, by the way, to clone. It's kind of cool. This is, okay, I told you this is like the super version of a fork. You can do anything you want. So you make your own stack, then you call clone with this clone helper function. I'm not kidding. This is like almost like I might have to fit on slides. I remove all error checking, all logging and all error checking and all comments. And then clone helper does a long jump back. So if you come back here, so this clone will call this function. That is what clone, you pass in the function that you wanted to call the moment it's finished. That does a long jump back here, and then it looks like a fork. This is like real Chromium code. You think I'm joking? No. Because they thought it was like, yeah, everybody understands how fork works, so we're just going to do it the same way. So this is how it does. Okay, anyway. Okay, so shrinking the initial sandbox. Okay, so we did that first part. Now we're going to make it even worse. Okay, so here we will have, first what we will do, there is a user namespace created here. It's using unshare. I'm not going to get into it. It does a lot of like capset stuff, but I'm not going to get into that either, I think, in this one. But I'm going to look at the chroot, and I'm going to look at the seccomp. And yeah, okay, let's see. We'll see. So basically here they're going to try to do different kinds of things for limiting the different kinds of processes. I made a longer version of this talk for the NDC conference this year, so and it's on YouTube, so you can find it. But basically, okay, so who's familiar with seccomp? Nobody. Seccomp is really cool. So seccomp is a mechanism which is actually, I probably wrote it here. No, I didn't. It was basically made to filter TCP packets. Because the problem is, if you're having TCP packets, there are just a whole lot of them, and you want to do filtering of just a few, then you want to set up some kind of rule set to say which ones you're interested in. And so they made a language for that. It is called BPF, Berkeley Packet Filter. So basically you write a program saying which packets you're interested in, and then you pass that program into the kernel, and it runs inside of the kernel in this tiny little VM. And then, because what you don't want to do is have a context switch every time you get a TCP packet. So because it's too expensive, so this is not going to scale, so it doesn't work. So now you've made this tiny little assembly-like program that says what you're interested in, and whenever there's a TCP packet, the kernel will run this little thing and then figure out, yes, it's interesting, no, it's not interesting. Yeah, that's what it was made for. But people found out that this was actually very useful, and we could use it for other things. And they made seccomp, which does the same thing for system calls. So now, when a system call, if you have installed a seccomp filter in the kernel, then when this program or a child program or, process makes a system call, the kernel will run it through this little VM and run your little program and figure out if this is okay or not. So you snip, 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 and you can cut off any access to any system call that you don't want. This is basically what makes all of these things sandboxy. Because we've made it, we've done some things. We've taken away network, we've taken away all the other users, we've taken away all the other programs on the system, so now you can't see any of that. You think you're living in this little world. Now we're saying, okay, well, you can't have any of the system calls either. And later we're going to chroot you. So it's like, and then it's like, oh, I don't know who I am. Anyway, so it's very, very cool. It's not very, on Mac they have something similar, and there they have like this nice files with like readable names and stuff. This is like absolutely horrid to read. You basically write it with macros. And so, of course, there's like classes for it inside of Chromium, so you never actually see it. So inside of Chromium, they have they call them policies. These things are compiled into BPF programs, which are then installed. And you can make these policies, because basically they're programs, so you can make them be whitelisty or blacklisty. Basically saying either, if you can think of it as a massive switch thing, you can say the default case is fail or the default case is pass. That is what goes in whether or not it's a whitelist or a blacklist. If you don't hit any of your rules, is it okay or not? In this case, in Chromium, it is a whitelist. That means that if there is no rule for this system call, it is not allowed. And then they extend them by subclassing. So because of this, an extended policy is more permissive, because you're adding stuff to your switch, which makes more things are allowed, because these things are not falling through to fail. Because what you can do in seccomp BPF programs is you can do a lot of different things. You can either say it's acceptable, just let it go, just let it pass. You can say it's unacceptable and I want you to fail in this way. I want you to have this kind of signal or that kind of signal or nothing, or fail very with an error code. But not only that, you can also look at the parameters to the system call, inspect them, and say that only when you pass null as the second parameter, then it's going to be all right. So you have very, very fine-grained control here. So basically here, so you'll see that there's a baseline policy that all of the sandboxed things get. And then the GPU process policy extends this, so it's more permissive. And the GPU broker process policy extends that one again, which is even more permissive. And then the render policy also extends baseline policy and is more permissive. Okay, yeah. So this is sort of how that looks code-wise. It's not very, like you will have like a policy that you pass in and you have like a concept of a sandbox, which is an object. But all of this is just kind of fluff around the Linux APIs. But okay, moving on. So we go to install filter. Okay, so here that's like assemble filter, and then you have a program. And then it will make a struct. And it will take the size of it. It's like this is now quickly decomposing from fancy high-level C++. And then, you know, and you have just a plain-ass mem copy. And it's like coming from the last talk, this is kind of like it's deteriorated rapidly here. And then you do this PR set no new privs, which makes this you can do this unprivileged, and then you install the seccomp filter here. And you install it basically by passing the address. And that's it. It's like really low level. There's like nothing there. This is like a chunk of memory. Here you go. It's not really made for like high-level programmers. Okay, and then we come to another cool thing that they use. Okay, this is Chroot. And they do a really fancy, cool little trick. And they're using clone again. Because you have a flag that you can pass to clone, which is called clone FS. Clone file system, I think it stands for. When you do a clone FS, this thing that you create will share your file system attributes. That also meaning it will share what is your current working directory, and and it will Chroot with you. So in this case, what they do is they clone FS a child process. Now, this is just very, very short. This process like lasts for like a function. In this child process, it Chroots to proc self fd info. This is a process-specific directory for this child. So when the child Chroots to this directory, because it has done, it was started with clone FS, the parent process also Chroots with it into a process-specific directory for the child. The child then does a cd to slash, which for them is that. So now they think they're in slash. The parent also did it with the child because they share. So now both of them are standing in thinking root is, the slash is this, which is a process-specific directory. And then the child exits. And this directory stops existing. And the parent is now Chrooted to a non-existent directory. And poof, and you have no access to the file system. Huh?
Aren't you overdoing this security thing?
I think it's really cool.
So is this very heavy? This clone call? Is this
No, no, I don't think so. But it's only done when you, this is, well, actually, I think it's in the next, no, okay, I'll get to it. Or maybe I should go back. Let's see. Let's see. This is done here, actually. I think it's this one that does it. Okay, I think it's in an, No, here, yeah, that's the cheroot. So this one is the one that does it, and there's only one of this, so it's only done once.
When
The
you
thing
start
is,
your browser.
all, yes. And then all of the children are trapped in this world where slash doesn't exist. Yes.
Why is the shoot trick better than just using seccomp and deny access to all file system?
The thing is, okay, this is more of a security philosophy that people have come to around things like sandboxing and jailing and stuff, is that basically saying that trying to target specific security bugs is hard because you don't know what they are, because if you knew what they were, then you would have fixed them. So instead, you're basically isolating as much as possible and basically saying if you escape, you're still trapped. And trying to take away whole force of attack vectors without necessarily knowing whether or not they're dangerous, but also saying that it doesn't hurt. And so in this case, these processes live in a world where they have no file system, where they have no network access. They think that they exist only with these processes that are running. They think that they have like fake users. These processes are living in a fake universe.
So the only thing, yeah, that's.
Huh?
They have pipes.
Yes, they have pipes to other things that have things.
Portal.
Yes. Yes.
But that's the only way out, the pipes.
Yes, but you can't do a system call on a pipe, but you can trick another process to doing a system call. Yes, and you have a similar thing here. They have different seccomp filters here and here. And generally, you will have that the seccomps are inherited. So if you fork or clone, because you did the no new privs, your children will inherit your disabilities, I guess, in this case. Your inability, there you go, to access things. So they will be equal. So you can't do an exec VE to try to escape these limitations. Okay, no. Let's
So
see.
isn't the seccomp point a weak point? So because it runs in kernel space and it runs some weird program. So if there's some bug in the seccomp, you can exploit it.
Yes. So because of that, and because they already, it's old. That's one of the things that they based on. It wasn't something they made up for this. It was something that had been in Linux for a long time. But also there are there are rules for seccomp programs. There are no loops. You can never jump back. You can only have so many instructions. So you have like a whole set of things that make sure that this thing will terminate. You can't just spin forever. But I did see an exploit recently that used another vulnerability to disable seccomp. But that was a vulnerability in the kernel that they did to disable seccomp to escape the sandbox. So the thing is, it's like not like all things. These are things to try to make something more secure, but you can never actually guarantee that anything is totally secure. That's the world we live in, kind of. Make it more difficult. Yes. Okay, so here you see the code for what I said previously. So you have a cheroot to safe empty dir. Again, you have to make the stack because clone, you have to do that. You pass in the function that you want clone to call, and you pass the clone fs flag. And then the parent will do the wait PID, because in this case, the child will call this function so the parent can wait. And then we look in the child function, and that's what it does. It cheroots to this thing, it changes the directory to /, and then it exits.
How many lines of code is it just to create the sandbox? About.
If you like, The thing is, if you take everything all together, it's probably really big. But if you take the actual important parts, not much. Okay, so now we've isolated all those processes. They have no longer any access to the file system. So that's mostly my talk. But if you want to go and look in your browser at how, like I've named some of these things now, like you know a little bit about what, in this case it says namespace sandbox, but it actually means a user namespace sandbox. And PID namespace, network namespace, seccomp BPF sandbox. Seccomp BPF sandbox supports tsync, which means it also applies to threads because it should, but that was a new thing in Linux. Yama LSM is another thing. It has to do with p-tracing, but I go through it in my talk. But basically, if you go to your this kind of URL in your browser, so you go to, for example, if you're in Chrome, you write chrome://sandbox, then you will get this kind of box up, and it will say yes or no on these things. And what is yes or no will depend on your Linux distribution and what kind of facilities that are available. So in this case, you can see what kind of sandboxing is in place. And if you want to dig more into security APIs, first of all, the Linux programming interface by Michael Kursick is really good for the general programming towards Linux. And he also has a course, which used to at least be called Linux Security and Isolation APIs, which is excellent. And then the rest of stuff is reading a Chromium and kernel source code, Linux man pages, and lwn.net. And any mistakes are definitely mine. And that is it. And one last thing before I stop, because this is a cause of mine, is that we all have teams, and we all make products of different kinds, and we are trying to make products for everyone in the world, and we need to make sure that they work for everyone. And if everyone are not represented in the room making the thing, then we're running a really high risk of it not being a good thing for those people. And we've seen that a lot in the last few years. We saw Snapchat repeatedly releasing features that did not work on people with dark skin. They released it to production, to users, to millions of users. Now, that you managed to get to the point where a dark-skinned person can't have a little wiggly thing on their head means you had no dark-skinned person at all in the pipeline here that just walked into your office and tried it at a certain point. We have things that don't work for women. We have things that don't work for people with disabilities. And the problem is that it's because people are either not in the room, or they're not brave enough to speak up when they are in the room, or when they speak up, we're not listening. And so I think what we have to do in this industry, and I think maybe especially in C and C++, because we're very male-dominated and very often leaning very hard to the white straight male angle, is that we have to be wary of these situations and try to listen to people. And some things you can tell, like if somebody's a dark-skinned person, you will generally know they are dark-skinned. But there are ridiculously few openly gay men in this industry, and that's a problem. Because if you had an openly gay man in your team, then he would also feel comfortable to tell you when things are not right. When things you do are openly homophobic, the products that you're making are in some kind of way offensive. If you have people who are transgendered, they will tell you that why the hell do you have to have a gender checkbox on your website? And they would say it. So what I'm saying is, for me, this is like really important. We have to make everyone feel safe to be themselves in our teams, so that what we make works for everybody and works also for the people who work with us. And so that is my last slide, I promise, except that you have to take the swag because I don't want to take it home. And try my browser. Thank you.